1 minute left. So welcome everybody. Today we have the great pleasure to have Professor Martin Wegener from the Karlsruhe Institute of Technology. We'll discuss about chiral elastic metamaterials. Martin, it's all yours.
Yeah, thank you very much, Sebastian. Let me share my screen and go into the presentation mode. I hope you can all see this. So this is going to be about three-dimensional chiral mechanical metamaterials. And as a disclaimer, I would like to say that this is not going to be some big review. I would rather like to focus on some recent results and bring these in perspectives just with a couple of things that are a bit older. In the last, let me start with this view graph here. First of all, I should like to acknowledge the people who have actually done the work. I highlight a couple of names, for example, Tobias Frenzel, who has started the chiral metamaterial business in my group. You will see results of Vincent Hahn, who has made some great technological advances that allow us to make very large metamaterials. Yi Shen has lately done some really interesting theoretical calculations, and apart from that, I should like to highlight the collaborating groups in alphabetical order: Sebastian Gounod's group, Peter Gumsch and Patrick Ziemke in his group, and Muammar Kadic. So some of these people are actually in the session here. Let me start with an introduction and define what a metamaterial is. We have seen a couple of definitions in previous webinars, and if you have really paid attention, you will have seen that they do not agree. This is not to say that I am God and I am now the person to define what really metamaterials are, but at least I would like to be precise what I mean by that. And to me, metamaterials are rationally designed composite. So some random stuff to me is not a metamaterial. This composite is supposed to have effective medium properties, not just some properties, but effective medium properties. And I'm going to dwell on that go beyond, in some sense, qualitatively or quantitatively, beyond the properties of the bulk ingredients. Notice that I do not use what many other people do, is that to say that this goes beyond what is found in nature. I find this very dangerous because you would be surprised of all the things that are in nature. If you take that definition, I would argue probably 99% of the papers that claim to be about metamaterials are not about metamaterials. So this is at least my definition. I hope there will be some convergence in the field. And these effective medium parameters are important to me because if, for example, you take a piece of silicon and you try to compute the refractive index, you will find out that's very, very hard to calculate actually from quantum mechanical principles. But once you have ignored all the atoms, all the quantum mechanical complexity, you can look at silicon as a homogeneous material, as an effective material, just use the refractive index, and that's how silicon photonics works, just for example. Now we take such effective media and we structure them in a periodic fashion or in a disordered fashion, whatever you want, or in a quasi-crystalline fashion. And we again build something out of it that we want to look at as an effective medium at the end of the day, such that for the user, it's basically indistinguishable at the end whether you have a material or a metamaterial in your hand. I'm going to be speaking about chiral metamaterials, just for those of you who do not work with chirality every day. Chirality means that you need broken space-inversion symmetry. It, in addition, means that you have the absence of mirror planes and the absence of rotation-reflection symmetries. And the absence of these symmetries allows you to do things, so to speak, get degrees of freedom or behaviors that are otherwise simply forbidden by symmetry. So a bit to effective medium theories in the context of mechanics. What you read in every textbook is Cauchy elasticity, which, if you want, is a generalization of Hooke's law. but the spring constant in Hooke's law is replaced by the elasticity tensor, which connects the stress tensor and the strain tensor. And as you all know, in general, the elasticity tensor contains 21 independent parameters that describe a lot of degrees of freedom that you can have if, for example, you take a beam and you push on it. There are very many things that can happen. The lateral cross-section can shrink, the beam can shear, many things can happen. But one of the things that will certainly not happen is that you observe any chiral effects on the basis of Cauchy elasticity. Now, you can look at this from different perspectives. Microscopically, if you look at the derivation of Cauchy elasticity, essentially one approximates the atoms or molecules in a solid by points. Some people don't like when I say this. Precisely, it's an infinitesimally small volume element. Nevertheless, if you take such a small element or take a point and you rotate that point, nothing happens. It's not really a degree of freedom. And that is microscopically why chiral effects are not covered by Cauchy elasticity. By the same reason that we describe the atoms as points, there is no scale in Cauchy elasticity. And as a result, people say it's scale invariant. There is no particular scale that appears in Cauchy elasticity, just like in the Maxwell equations. And as a result, it doesn't really matter how many atoms you have in a solid. If, for example, you double all dimensions by a factor of 2, the behavior is going to be just the same. If you look at time-dependent phenomena, it's going to be slower by a factor of 2, but nothing else happens. And these two things are connected. Point mechanics means you have no chiral effects and you have an invariance of the scale. And as a side note, I also say that Cauchy elasticity is not form invariant, but that is not important for my talk. If you do not like this explanation, you can also just look at Cauchy elasticity mathematically. And remember that when you perform a space inversion, you go from R to minus R. This means you go from a left-handed to a right-handed material. None of these tensors changes. They are all even ranked tensors. Every even ranked tensor is invariant with respect to a space inversion. And that means this equation doesn't even know whether a medium is left-handed or right-handed. And as a result, it can never describe any chiral effects. Now, there are various generalizations of Cauchy elasticity. I'm going to be speaking about only Ehringen micropolar elasticity, which goes away from points and describes the atoms or whatever you have in your solid as finite size elements. And as a result, you do not only have one tensor, but you have 4 different tensors. I will come back to that. This allows you to describe chiral effects, but at the same time, Ehringen micropolar elasticity is not scale invariant. And that means that all the effects are going to depend on the size of the sample that you have in front of you, because there is a particular scale, a characteristic length that enters into Ehringen micropolar elasticity. And I've repeated this point in this little table. To the best of my understanding, these 2 points, chirality and a loss of scale invariance, are intimately connected. All right, this brings me to the systematic part of my talk. I've divided it into 2 pieces, some results on the static regime and some results on the dynamic regime, that is about wave propagation in chiral elastic media. I start with a static one, and I start with an image that we had in a paper we published 3 years ago. That was just to say that there is an infinite number of chiral lattices or metamaterials you might consider. We have considered a few. I make no claim that we have considered all of them. And I make no claim that we have considered the best. But what we have considered has gotten pretty good, I would argue. And our favorite structure is shown in panel A, and I magnify it in this view graph here. It's derived from a cube. And on each face of the cube, you see a ring. And then the ring is connected to the corners by these 4 arms that you can see here. And it is exactly that connection that makes the unit cell chiral. The fact that you have this angle that we call delta here with respect to the phase diagonal means that the structure has no center of inversion, it has no mirror symmetries and no rotation mirror symmetries, and it becomes chiral. So once we make this angle delta 0, bring this thing into the phase diagonal, the structure becomes chiral, and I'm going to be using that as a control experiment later on in 2 contexts. Okay, how does it work? It's pretty simple. If you look at this cell and you look at the side and you push from the top, then by this lever arm here, you're going to rotate this ring a little bit. And this rotation is going to pull down this corner. And as a result, if you look at the unit cell from the top, it's just going to rotate. I mean, the top surface is going to rotate. The bottom surface is not going to rotate. So it's a twist that you get, but the center of mass stays fixed. This is important for what follows. There's a twist, but the center of mass stays exactly constant. Now, looking at a single unit cell is boring. What we really are interested in are materials, crystals in 3 dimensions, such as this thing here. And as soon as you now hook up these cells to a solid, the story becomes highly non-trivial. And let me explain this in a simple intuitive picture that I'm later going to refine a little bit. If you look at a single cell and we push on it in a direction normal to this projection plane here, it's going to twist, say clockwise, as I have described before. Now, if I plot more unit cells, in this case 3 by 3 unit cells seen from the top, and I'm going to call this n equal 3, and I do not connect the cells at all, they're just sitting side by side without any connection, then they're going to do exactly the same thing. But as each center of mass is fixed, these micro rotations are not translating into anything. They will in particular not lead to a macroscopic twist of the sample. The micro rotations do not translate into a macro rotation at all, and then as a material you will have 0 effect. So the next try is to connect them directly, so to speak, glue the cells together. The issue then is, as you can see here, is that the displacement vectors that we have plotted in red are in opposite directions of the adjacent unit cells, which means the displacements are going to cancel at these interfaces here, which means the only displacements that you are left with are the ones at the surface, which already tells you that the effect at the end is going to go like the surface to volume ratio of the solid, and that goes like 1 over the side length. This would be the side length, or in other words, like 1 over this quantity n that I'm going to use a number of times. Perhaps you get used to this. So n for me is not the total number of cells, it's the number of cells in any one direction here, 3 in this particular example. So then the effect is going to decrease, again, like the surface to volume ratio, like 1 over n. And if you go to large values of n, which is, so to speak, the Cauchy elasticity limit, in which the unit cells are again going to look small, going to look like points, these chiral effects disappear, just very qualitatively speaking. How do we make these samples? Many of you may know this. We are using a technique called direct laser writing or 3D laser nanoprinting, in which we take femtosecond laser pulses, and I stop this movie here, and in the focal volume indicated here, a chemical reaction is induced, which often, not always, but often brings you from a liquid monomer material to a polymerized polymer material, which is solid. And then we scan. I just keep on going with this movie here. You do whatever you want by computer control. And at the end, you take a solvent that can be as simple as acetone, and you wash out the insufficiently polymerized material, the liquid stuff, and you get a solid structure on a substrate. The principle is as simple as that. If I go back in the movie a little bit, I'm going to be using a word very often. I'm going to call this thing the voxel, the volume element, the smallest volume element that we can reproducibly make. In a general context, I call it the voxel, and it's called like that in analogy to the pixel, the two-dimensional graphical pixel that you know from your LCD screen, etc. The picture element, the voxel, is a corresponding volume element. It's, so to speak, the smallest Lego block that we can use to build up complex three-dimensional architectures. So this is an example that Tobias Frenzel fabricated a number of years ago. We have a chiral structure, and there is a little trick that you will see a number of times. If you push on this thing here and you want to see a twist, you would need sliding boundary conditions. And that's an ugly thing on the micro scale. And as a result, we have taken a left-handed structure underneath a right-handed structure, such that the total twist is 0, the total torque is also 0, and only this middle part here twists. Then we can have fixed stamps on both sides. In fact, these twist arrows here are not just drawn by me by PowerPoint, but they have been measured directly by optical image cross-correlation analysis. We have magnified them a little bit, but we have magnified them by the same factor that we have used the compression arrows here. So here the twist effect, in other words, is as big as the ordinary compression effect. So to speak, we have made a forbidden effect as large as the usual Hooke's law effect that you would look at. Here you see the A film, how Tobias has arrived at these data. You can even see it with your bare eye in the linear elastic regime. This twist effect on the right-hand side, you see the ordinary compression, and it's fully reversible under the conditions that I tell you here. Now, we expect size effects, and as a result, Tobias has made different samples that have the same overall size, but that have a different number of unit cells in them. This one has n equal 1, n equal 2. You also see it here, n equal 3, n equal 4, n equal 5. Again, the outer dimensions are the same, but the number of unit cells are different. And we do this because in Cauchy elasticity, you would expect that you get absolutely no change. To show you that we have done a good job in scaling the unit cell, I show you here electron micrographs at the bottom, in which Tobias has increased the magnification by 2, by 3, by 4, by 5, such that these cells should look the same in the PowerPoint presentation if we have done a perfect scaling. And I would say he has done a pretty good job. Now, based on such samples, we have made experiments, and we have observed the twist per strain. We normalize the twist. I mean, it's in the linear regime, it's just proportional to the force that you apply. So we normalize it to the strain, twist per strain in units of degree per percent. And we plot this as a function of this quantity n, which is the number of unit cells in one direction. So we go from 1 to 5, and 5 means a total of 500 unit cells for our parameters. What you see is that there is a small decrease of this twist effect by about a factor of 2. You see that the achiral control structure has no twist effect. That's trivial. That's just a sanity check. And you also see that the effective Young's modulus changes. And that's the size effect I was talking about. That comes from this compensation effect at the inner interfaces I was talking about. And if we go to the achiral control, that behaves as you would expect from Cauchy elasticity, in that the Young's modulus does not depend on the number of unit cells in your specimen. But for the chiral structure, there's quite a strong dependence. It's about a factor of 10 almost, that the Young's modulus changes here from 3 perhaps to almost 30 in the experimental data points. What you can also see is a number of calculations. We have finite element microstructure calculations. These are these symbols that agree quite nicely. And I'm also comparing the result of Ehringen micropolar continuum elasticity. These are these solid curves, and that also agrees quite nicely with the experiment. I'm going to come back to the mathematics later on. Again, to continuum theory, if you compare, just for one example, the behavior of the continuum with a microstructure, you can see that the continuum grasps these effects quite nicely. And once again, I'm repeating myself, I know in Cauchy elasticity, this twist effect would be 0. Okay, so later I'm going to show you samples that are a lot bigger than what I've shown you so far, and that is due to some progress in 3D laser printing that Vincent Hahn has lately made, and I'll show you some results from this paper. just in case you care a little bit about fabrication. The main point is that instead of one laser focus, we use an array of laser foci, in this case 3x3 laser foci, and in addition, we scan the laser foci faster than we usually do. That's how we get a tremendous speed advantage. I'm showing you here a terrible view graph if you have never seen it before, which gives you a flavor for where we stand. This view graph summarizes all kinds of 3D printing technologies that I'm not going to read to you, and it plots the total peak printing rate in voxels per second on a logarithmic scale. These are 9 orders of magnitude here on the vertical scale, versus the inverse voxel size, loosely the resolution. If you don't like this, you also have the voxel size in absolute terms at the top. So this goes from 10 nanometers on the right to 1 millimeter on the left-hand side. The technique I'm showing you here provides submicron precision, submicron feature sizes, and resolution. And if you look at this regime, actually there are not so many techniques left that allow you to do anything. This is this 2-photon-based 3D laser printing, the red symbols. There is electrohydrodynamic printing, and there is electron beam induced deposition. And you can see these are many orders of magnitude slower than the fastest that we can do at the moment. So perhaps I say this, if you need about 1 minute to fabricate some particular structure here, it would literally take you 20 years to fabricate the same thing at this printing rate. And I argue that the rate in terms of voxels per second is really what matters. That is the rate by which we, so to speak, convert software, convert digital information into hardware. A 3D printer is nothing than a converter of software to hardware at the end of the day. And that's the conversion rate by which we do this. And in this paper by Vincent Hahn, we have now arrived at 10 to the 7 voxels per second. This stuff here, 10 million of these little Lego blocks per second that we make. And by doing that, we can now make much bigger structures, in particular with many more unit cells. This is a specimen that has more than 100,000 of these chiral unit cells that I've shown you before. It is composed of more than 300 billion voxels. It's really a large number, 300 billion voxels. I could show you anything with this yellow blob here, but if you take a Heine laser and you shine it onto the structure, you immediately see the Laue diffraction pattern, showing you that this is a nice, well-organized crystal that we have made here. And if you still don't believe it, you can take a larger magnification. Now you can start seeing the unit cells here a little bit. And now I think people who have previously argued that metamaterials are not really materials, they look like model structures, should eventually shut up. To the best of my understanding, this is a material like any other material is. And if you want to get a feeling for the quality, you can look at some electron micrographs of this particular structure, and you see that the quality is pretty cool, I would say. Okay. Next, I'm going to be using this technology to look at some interesting physics. And I'm coming back to the aspect of connection of the unit cells. So what I told you so far is that the twist per strain, if plotted versus this number n, we sometimes call it the scale factor, or it's simply the number of unit cells in any one direction, scales eventually like the surface to volume ratio. That is, it scales like 1/n. And in fact, this very old calculations from this science paper shows you that the calculated behavior by Ehring micropolar elasticity follows this expected scaling. And this is in a way frustrating because it tells you that these effects decrease as you go to larger and larger specimen, and you may want to make larger materials and still exploit chiral effects. Now, to the best of my understanding, this asymptotic decrease is fundamental, and you can do nothing about this. But you can shift this decay on this axis as you wish. What I want to show you next is that you can get a behavior that doesn't start with a decrease, but that starts with a very large increase first. And then only at large samples, eventually you come into this asymptotic regime. That's the next point. We want to drastically change the qualitative behavior. And we have started looking into this in this paper with Patrick Ziemke last year, but I'm not going through that at all. I just want to show you some more recent stuff that is not even submitted yet. And that uses a unit cell that is derived from the one I've shown you previously. The blue stuff is exactly the same as I've shown you before, but now we neither do not connect the cells, nor do we directly connect the cells, but we connect the cells by these red elements, by these elongated beams, to intentionally get a loose connection, an elastically loose connection between the unit cells. And I want to show you that by changing this lever arm, you can actually change the behavior in principle as you wish and make the characteristic length as large as you want. So naively, you can think about it as a compromise, once again, between not connecting the cells at all and rigidly connecting the cells. And this compromise gives you a totally different behavior. And this is the same cell, just from a different perspective, that you get a decent feeling for how it looks. Now, before I show you some results, I want to give you a bit more of an intuitive feeling by quickly jumping into a simple model that we have cooked up. And the main ingredient of this model is illustrated on this view graph. If you take a single unit cell, this one here, and now you staple, in this case, I believe 15 unit cells on top, then what happens is very simple. This unit cell gives you a certain twist angle, and if you staple 15 unit cells, you will get 15 times this twist angle. It simply adds up the twist angle. This is totally trivial. 15 cells in this row give you 15 times the effect. And the same is true if you take 15 layers and staple 15 layers, you're going to get 15 times the effect. But the effect you get from a single column and the effect you get from the overall crystal are not the same, because this cell here, for example, couples to its neighbors. And that's why this angle here, this phi angle, is different from this var phi in Tech nomenclature angle. And this leads to an elastic energy, because this column cannot twist as it wants, but it kind of is forced by the neighbors to twist by a different angle, gives rise to an elastic energy contribution that goes like the difference of these angles squared in the linear elastic regime. And that is the crucial component that determines the characteristic length. Let me briefly show you the mathematics. It's comprised of two contributions to the energy, to the elastic energy. Two are trivial, totally well known. One is the compression energy. It scales like the volume or this quantity n cubed. One is the twist energy of the specimen that you get regardless of whether the sample is chiral or not. Again, it scales like the volume. And you get the term that I have just discussed. You get the difference between these two angles, between the angle by which a single column wants to twist and the angle by which the metamaterial actually twists. And this angle by which the column wants to twist is proportional to the number n, as I explained before, where gamma is basically the twist angle of a single cell, literally. The rest is totally straightforward. You look for the minimum of the energy, you work it out and order the terms, and you get a very simple expression. You get that the twist angle as a function of n has this dependence here. So first of all, you see it is proportional to the twist angle for n equal 1. That is, so to speak, a prefactor. And quite obviously, this angle is a property of the single cell. It has nothing to do with how the cells are connected. This is a property of a single unit cell. But there is a second property that appears in this twist angle here on the left-hand side, and that's the characteristic length. It's defined on the right-hand side. Actually, I use it as the characteristic number, which is a length divided by the lattice constant. I like this characteristic number better because it's size independent, this statement here. And it comes about from the ratio of these two coefficients that you have seen. Maybe you want to go back. So it goes like the square root of C3 over C2. So what you want is, you want a strong connection between adjacent unit cells, but on the other hand, you want the sample to be easily twistable. And if you think about it, this seems at first sight like a total contradiction. In fact, these two things tend to go in the same direction, yet you can play a lot with the ratio of these quantities. But what becomes clear is that the coupling of the unit cells determines this characteristic number. Now, this expression has a very simple behavior. If you just look at it here, it goes proportional to n as long as n is smaller than the characteristic number. Then you can simply take, then this squared here is small compared to this guy, and the nc square cancels out. It just goes like this n here. That's what I plot here. Then as n becomes larger, there will be a maximum of the twist angle. That's at this condition. And then for very much larger n, larger than the characteristic number, you're going to get this 1/n decay that I have claimed previously to be fundamental. And we again get it. And this brings you back to Cauchy elasticity, because for n equal to infinity, you again get 0 twist effect. If you find this too abstract, that's the same thing visualized in terms of a plot. I plot here the normalized twist angle as a function of n, the number of unit cells in the x or in the y direction. And you see that for small characteristic lengths, and that's pretty much what we discussed in the science paper, you immediately get a decrease and you get into this 1/n asymptotic decay. But then as the characteristic number increases, you first get a linear increase, you get a maximum, and then only eventually you get this asymptotic decrease. But the prefactor in front of this asymptotic decrease has totally changed. It's nc squared. So you get a huge difference here between what you would get for a characteristic number of 1 and say a characteristic number of 2 here. This is a tremendous difference. And this allows us to bring these twist effects to a specimen that contain really a large number of unit cells. Now, how does that look in the experiments? Here I have a little gallery of structures that Tobias Frenzel and Vincent Hahn have made using this multi-focus, multi-photon 3D laser printing. You see again samples with different values of n. Again, bear in mind, n is the number of unit cells in any one direction. So when we go to n equal to 27, what that means is that we have about 120,000 three-dimensional unit cells. And you can see an electron micrograph here on the right-hand side, or a further magnification here with all these details. And the most important point for these kind of structures is this lever arm that connects adjacent unit cells. They are only connected in plane by these arms here. These faces do no longer touch. Now, this is a bit of a terrible view graph because it's too full, but it summarizes a lot of results. It summarizes experiments. These are the symbols here. The first impression perhaps that you get is there's a lot of scattering. Well, there is quite a bit of scattering, but these different symbols correspond to different strain values. If you look carefully here, the strain values are given. There is a fair amount of nonlinearity. And in fact, the nonlinearity becomes larger as this scale factor increases. If you ignore this for the moment, the main trend is that the experimental data give you an increase that is also magnified, shown here in the bottom panel. It's the same thing, just for a smaller range of n, values for n. You see a linear increase followed by a maximum, and then eventually you get a decrease. And this gives you numbers in this regime that are much larger than what we have previously gotten in the science paper that I showed you. This is just for reference, the science data again, with the science parameters for the area and micropolar elasticity. Beyond that, I compare a number of different theoretical approaches here. You will find, for example, these symbols, these orange symbols, are pretty much complete finite element, volume element calculations. There are Timoshenko beam calculations, because there's no way you bring these finite element calculations to these large numbers of unit cells. Again, 27 means 120,000 unit cells, and this you can only get close to by doing drastic approximations like using this Timoshenko beam approximation that still gives you the same trend. So I would say this tailoring of the characteristic length here to a value of about 10 has been observed experimentally. With this, I should like to switch gears and speak about similar structures, similar metamaterials, but the dynamic regime, wave propagation. And we call this acoustical activity because it is the counterpart of optical activity. So let me start with something fairly obvious, just to be clear. If you have a chiral medium, you expect that the eigenstates of the medium, the phonons, so to speak, are also chiral. Or yet more clearly speaking, you expect that the usual linearly polarized transverse acoustical phonons, the TA phonons, are not eigenstates of the system. You expect chiral eigenstates. And what this means is that if you send into such a medium a linear polarization, a TA phonon in solid physics jargon, then you have to decompose this linear polarization into right-handed and left-handed eigenpolarizations. They propagate with different velocities, which is written down here. And this means that this linear polarization is eventually going to rotate by a certain angle, theta here, that is given by the difference in wave number of these modes at the frequency that you consider. And of course, it is proportional to the propagation distance. It's exactly the same formula that you would write down for optical activity. It's just the same thing. Just to be clear, acoustical activity has been discussed in the context of ordinary crystals. To be honest, I have not heard about this term until a few years ago. That's why we originally also spoke of mechanical activity. We mean the same thing. But in the literature, several papers have discussed on the level of continuum theory acoustical activity by these different approximations that I've written down here. There have even been experiments, big surprise, quartz, which is a good material for optical activity, also gives you some acoustical activity if you look at the right phonon propagation direction. But the thing is that the effects are very small. And more importantly, you cannot tune these effects to the frequency that you want. They would be maximal roughly at terahertz frequencies. But if you want something big at kilohertz, megahertz, or gigahertz frequency, there's no way you can change an ordinary material to get the maximum effect where you want it. So that would be the point of using a metamaterial here. I'm again going to be using this same unit cell. That's what Tobias used. And now I'll start by showing you a pretty busy view graph, but I believe it's important to get an overview. The first row shows you the chiral result. You see a beam composed of 1 by 1 unit cell, another beam composed of 3 by 3 unit cells. This would be n equals 3 in my nomenclature, and infinite by infinite unit cells. This would be the bulk. And for reference, I show you in the bottom row here the achiral controls. If you have a good eye, you see that here this connection element is along the face diagonal, and this structure is not chiral. What you see for the achiral structure is pretty boring. You get two transverse band TA phonons that are degenerate for propagation along the axis here, along the z direction. That's a cubic axis. And you see that there's very little action if you change the cross-section of the beam. That is, there's very little action if you change the size of your specimen. This is distinct from what you get if you go to the chiral counterpart. First of all, you see there is a splitting here. And this splitting, that's the splitting in momentum I'm showing you here. This will give you the rotation angle at this frequency, this delta k here. This splitting is pretty large, but it depends on the number of unit cells, quite obviously. It's very much larger here than it is here for the bulk limit, but there is a finite effect that survives even in the bulk limit for infinitely many unit cells. And that is because here the wavelength is no longer infinitely large compared to the unit cell. So that's what we expect. And once again, as I said, we expect that the eigenstates are chiral phonons. I'll show you these eigenstates here just for example, but more or less they look all the same. And that's a nice movie that Tobias Frenzel has made, in which you see a visualization of chiral phonons. They rotate. So if you look at any one unit cell and at its center of mass, it describes a circle around its rest position. The different unit cells are phase shifted. So if you plot the unit cell position as a function of time and space, you get this helix on the right-hand side. This is exactly the same thing that you would get for circular polarization of light in electromagnetism. Now here for phonons. Maybe a difference is that for this rotation to happen, the adjacent unit cells must deform. They must shear, and that's how you get this a little bit psychedelic motion of the unit cells in this eigenmode of the chiral crystal. The way we measure this is by rotation of the linear polarization, and I want to be a little bit short on this side here. By excitation with a piezo, Tobias Frenzel has excited the sample as shown on the bottom. By using stroboscopic illumination and image cross-correlation, actually these lines here are measured. I'm not just drawing them by PowerPoint, but this is the polarization of the phonon that impinges on the bottom of the sample. Then it propagates upwards, and on the top we again measure the polarization, and you can see it is rotated by roughly 45 degrees in this particular example. Be clear that this is a totally different scale here. These are fairly small displacements. We have just magnified them that you can see them, but you can also see that we can measure directly in the experiment the displacements on a nanometer scale. We can measure the polarization directly. We measure the displacement vector, not just some number in this experiment here. Here are some raw data, just in case you don't believe this. You see some displacements here with a peak amplitude of 20 nanometer or so. You get some reasonable noise here. We plot X versus Y on the right-hand side. This gives us this top polarization. Same thing at the bottom. You again see the raw input data on the left-hand side. And this is how we measure the rotation angle. That is a smoking gun evidence for having acoustical activity. That is for having chiral phonons in the structure. We've done this for many different samples. We have done this for many different frequencies. Perhaps I cut this short here. I'm a little bit running short in time. You see that the rotation angle depends on frequency. That is no surprise. In the long wavelength or zero frequency limit, actually there is strictly zero effect left. For the experts, this is a k-linear term at the end of the day, like optical activity in electromagnetism. It is proportional to k, it is proportional to omega, and for omega equals 0, you get no effect, strictly speaking. And you also see that the effect is again sample size dependent. It depends a lot on n, and this is again a fingerprint of Ehringen micropolar elasticity, as I tried to explain in the very beginning. Can we get larger effects? Yes, and I really cut this short. We have different crystals. If you care, ask me later on. The point that I would like to say a little bit about is the mapping onto continuum models. And what we have done is we have used Ehringen micropolar elasticity. Just as a disclaimer, this is not by us. This is in textbooks that are well documented. For example, this one by Cemal Ehringen here. Just for those of you who do not work with that every day, I have this comparison here between electromagnetism and mechanics. In electromagnetism, I was educated in that everything that you need to know in optics is in the dielectric function, epsilon, which describes the coupling of the E field and the D field, or in other words, the coupling between, or the excitation, I should say, of electric dipoles by the electric field. And you can forget about everything else here. That's what I learned in my optics courses. And that is correct in the strict limit that you look at the atoms as a point. And likewise, it is correct in mechanics too. Cauchy elasticity, which is this part here I'm circling around with my cursor, is exact if you are in the long wavelength limit and if you have a sample that has an infinite size compared to your atoms. But because of the finite unit cell size, there are additional terms like the magnetic permeability in optics, The analog of this would be this tensor here, which connects torques to twists. But more importantly, these cross terms here that couple magnetic dipoles to, electric dipoles, I should point to the left-hand side, that couple electric dipoles to the magnetic field, or that couple magnetic dipoles to the electric field, that give you chiral effects. And the counterpart in mechanics is a coupling between translational degrees and rotational degrees of freedom that give you these two entries here. And you can easily convince yourself, if your medium is chiral, then these two red marked tensor elements are all 0. It's the same thing in optics, except that optics is much simpler. There, all the tensors have half the number of indices. Mechanics is a lot richer because you also have longitudinal excitations in mechanics. This, in a nutshell, is Ehringen micropolar elasticity. It comes with a lot of parameters. For the conditions I show you, we have 12 independent non-zero parameters compared to 3 parameters in Cauchy elasticity for the cubic case. And you might argue that I can fit anything. Here's an annotation request. Let me approve this. You might argue, that this number of 12 here is a very large number, and you can fit anything with that. Well, that's not quite true. I have to get out of this now, otherwise I cannot scroll forward. There are a lot of bounds on these parameters because the elastic energy density must be positive for stability reasons. I've just written it down here. And if you work this out, you get a crazy number of conditions between all these parameters, which means you're not free to choose anything that you want. And there are additional bounds. Now, Yi-Shen has worked this out again for the example of this unit cell, which I'm focusing on in my talk here. And here you see a complex comparison. In the top row, you see again calculated microstructure band structures, pretty much the same that I've shown you before. You get the size effect. It's totally different for n equal 1, 3, 5, and the bulk limit. And in the bottom row, you now see the result of Ehringen micropolar elasticity. And it's not perfect, but if you look at the qualitative trends, that here you have a large splitting that becomes smaller and smaller to the right, it's actually quite good. You almost get the splitting here quantitatively right. Of course, you cannot expect to get the proper behavior if you go to the edge of the Brillouin zone. That's really stressing any continuum description as much as you can stress it. But even then, it's not totally off and gives you a fairly good description. Now, this is for one propagation direction. If you go to the bulk and you plot the direction dependence, which we have done here, it actually looks pretty cool. At the top row, you see the microstructure calculations. In the bottom, you see Ehringen micropolar elasticity, and it's spot on. But this I do not find very impressive. What I find very impressive is the following. And this is a bit complicated. This is a plot that shows you the polarizations as a function of the wave vector in 3 dimensions. So this is a plot in wave vector space. You see the 3 axes here at the bottom. And on a sphere in wave vector space, we plot the polarization corresponding to the point corresponding to a certain direction in momentum space. So this here, where my cursor is, would be a principal cubic direction. And in this principal cubic direction, we get circular polarization. That's what this circle means. As soon as you go away from this cubic direction, you get again linear polarization. This might confuse you, but if you look into it, what you need for circular polarization is a propagation axis that has at least a 3-fold or 4-fold rotational symmetry. Of course, if you go to any weird direction, you do not obey this condition, and big surprise, you get again linear polarization. For many, actually for most of the propagation directions, you do not get chiral phonons, but only for the principal cubic directions. That's what I showed you so far. And that is very nicely reproduced by Ehringen micropolar elasticity, as you can see here. And that is very highly non-trivial. If you have a good eye, there are also the space diagonals here. There are 4 space diagonals that have 3-fold rotational symmetry. And here in a very narrow range, you also get chiral phonons in this chiral lattice. This raises the question, and I'm coming to an end, I'm running too long here. Can you get chiral phonons for all directions of propagation? And this is something we have thought about for quite some time. And one solution that we have come up with has been published in this paper here a couple of days ago, and I'm going to be very quick on that. The idea has been stolen in a way from the literature, which has speculated that in quasi-crystals, instead of crystals, you can get isotropic properties. This statement has been made for achiral architectures, so we now want to translate this to chiral architectures. But that's where the inspiration comes from. Now, this is a little difficult to communicate in just a few minutes if you have never heard about quasi-crystals. Perhaps a beginner's course, you can think of a quasi-crystal in 3 dimensions as a 6-dimensional simple cubic crystal that you rotate in 6 dimensions by a certain angle that is connected to the golden ratio, which in a certain way is the most irrational number in mathematics. And after you have rotated it, you project it to 3 dimensions. While you don't project everything, you only project a part that is in the Wegener Seitz cell in an internal space. That's the basis of the, in principle, well-known cut and project method. That's how you can get quasi-crystals. Now, the issue is, in a way, we want quasi-crystals. In another way, we do not want them. If you have a quasi-crystal, you have no translational symmetry, and Bloch's theorem does not apply. You cannot use Bloch-Floquet boundary conditions anymore, and then computations become really, really hard. We would like to maintain Bloch periodic boundary conditions, and that's why we use approximations to quasi-crystals that are known as approximants. They do the same thing, basically, but you do not rotate by an angle connected to the golden ratio, but by an angle connected to an approximation of the golden ratio, which you can find by taking the ratio of successive Fibonacci numbers. So you get these rational fractions here. I would think this is very difficult to digest if you have never heard about this, but the bottom line is what we do is we construct ourselves a crystal that has a larger and larger lattice constant as we increase the order of the approximant. The interior of the unit cell becomes more and more complex, but then we approximate a quasi-crystal by doing so. And on the way, we can always use Bloch periodic boundary conditions. This gives you a little bit of the flavor how this goes. This is the unit cell here for the 1,1 approximant, and then it becomes more and more messy as we go to the 5,3 approximants that we have actually been using. Now, this is not a chiral lattice yet. So this aspect is illustrated here. After the cut and project method, you have this seeming mess of points that are connected here. If you stare at this for a while, it's actually not a mess, but you can think of these points as being composed of 2 types of rhombohedra that are shown here. Then all of these corner points lie on these rhombohedra. As I think this will be very difficult to digest, let me show you this picture. In 2 dimensions, you have probably seen something like this. The famous Penrose tilings are just like that. There you have this dark blue rhombus, you have this light blue rhombus, and you can cover the entire plane in a quasi-crystalline manner. We do the same thing, coming back to the same image, but now with rhombohedra in 3 dimensions, which makes the visualization a little bit more difficult. Now, this is again not chiral. The next thing that we do is we connect these points by the lines shown here, And in order to increase the coordination number, we not only connect them directly, but also by the phase diagonals and by this body diagonal. And then each and every line here is going to be replaced by this, if you want to call it a meta element, by a chiral element. We place this thing onto each line in this diagram. And what you get will look like this. This is this part here. Now we have replaced every line by an element like that. If you think that is messy, then look at the unit cell that we get. It's a fairly complex unit cell that we arrive at. Now this will be pretty much the last view graph here. Bottom line is it works. If you go from the left to the right, you see that on the left, again in this representation where you see the polarizations on the sphere in momentum space, you get lots and lots of linear polarization. But if you go to this higher order approximant on the right-hand side, you see that now, at least approximately, we have circles all over this sphere here, which means that we have circular polarization or chiral phonons for each and every propagation direction in 3 dimensions. Admittedly, with a very complicated architecture, and we are presently looking into ways to simplify that and bring it to experiments. Perhaps the last thing here, if you look at the relative frequency splitting, which is a measure of the chirality, that also converges from something totally anisotropic to approximating a sphere as far as we can go in the numerics. With this, I come to the end. I should like to acknowledge all the funding bodies that have allowed us for doing this research. And I summarize by showing a couple of images from my talk. Thank you very much.
Thank you, Martin, for this wonderful talk. Please feel free to ask any questions you wish to Martin.